Hello all and Happy New Year. In the last series, we discussed about the geocentric and heliocentric model used to represent the solar system. We also discussed of a small experiment that one can use to prove that the heliocentric model is better and right way to represent the solar system than the geocentric model. I hope you like that. So now in this series, we will discuss about the astronomical distances. By astronomical distances, I mean the distance between celestial bodies such as stars, galaxies, etc. So now let's first start off with the units. On Earth, to measure the distances between two two points, we use units like kilometers, meters, miles, nautical miles, etc. But can the same units be used to measure the astronomical distances? Now let's consider a few of the shortest distances we know. The distance between Earth and Sun is about 1.5 into 10 power 11 meters. The distance to the closest star is about 39 into 10 power 16 meters. If you consider the diameter of Milky Way, then it is of the order of 10 power 21 meters. While the distance to Andromeda galaxy, I believe you know what is the Andromeda galaxy. So distance to that galaxy is about 2.4 into 10 power 22 meters. And these are few of the shortest distances known. And the values keep on getting bigger and bigger as we move further out. So now we can't use these units, kilometers or meters, to represent these distances. We need some bigger units. So now here I have written down some of the units which are used to represent the astronomical distances. Now, light second is the distance traveled by light in 1 second. So the speed of light is about 2,997,92,458 meters per second, which is approximately 3 into 10 power 8 meters per second. So the distance covered by light with that speed in 1 second is 3 into 10 power 8 meters, approximately. Now, 1 light minute is the distance traveled by light in 1 minute, which is approximately equal to 3 into 10 power 8 into 60, which is equal to 1.8 into 10 power 10 meters. One astronomical unit, or shortly AU. Now here do not confuse between astronomical units and angstrom units for AU. Angstrom units is a totally different unit than the astronomical unit, and it is used to represent totally different objects, totally different distances. Now the astronomical unit is the distance between sun and earth, which is nearly equal to 1.49 into 10 power 11 meters. So that is equal to 1 astronomical unit. And if we convert this distance into light minutes and light seconds, we get that this distance is equal to approximately 8 light minutes and 20 light seconds. Now, 1 light hour is the distance traveled by light in 1 hour, which is approximately equal to 10 power 12 meters. 1 light year is the distance traveled by light in 1 year, which is equal to 9.5 into 10 power 15 meters. Now, the biggest unit of all these is the parsec. So, the definition of a parsec will be given in the upcoming videos. In this video, I haven't provided the required information to define a parsec, but I will just give you the value of a parsec, which is 3.26 light years. So 1 light year is 9.5 into 10 power 15 meters into 3.26, which is equal to 3 into 10 power 16 meters. Now, to measure larger distances, we use units like kiloparsecs or megaparsecs. Now, let's move further. So, now we know the units, but then how do we calculate the distances to the stars or galaxies or molecular clouds or any other celestial object? Now, on Earth, we use methods like using a meter tape or similar methods to calculate the distances. But can we use these same methods to calculate the distances to a star? Well, I believe you also know that this would be stupid idea. To calculate distance to sun using a meter tape is a really stupid idea. So we use various techniques or methods to calculate the distances, and using a meter tape is not one of them. So now which method can be or should be used depends on the resources available. So there are different resources which one can get looking at the star. We can see the luminosity, temperature, etc. So based on whatever resources we have, one has to decide which method he can use. Also, another important factor here is that how far away the body actually is. There are some methods which can be used to calculate distances to nearer objects, but if it's a far away object, then that method is useless. So we also have to decide based on that which method can be used. So here I have noted down the methods which are currently in use to calculate the astronomical distances. The parallax method, HR diagram fitting method, use of the Cepheid variables, the galaxy rotation rate, use of the type 1a supernova explosions, and use of the Hubble's law. Now, the top two methods, parallax method and HR diagram fitting method, can be used to calculate distances to stars. But the bottom four method, the Cepheid variables, galaxy rotation rate, type 1a supernova, and Hubble's law method, these four methods can only be used to calculate distances to galaxies. When it comes to calculating the distances to stars, these methods cannot be used. So now, between parallax method and HR diagram method, the parallax method is used to calculate shorter distances, while HR diagram method can be used to calculate farther away distances. Now, you can see that in the diagram shown here. So, we'll start from the bottom. So, one can use the radar ranging, use of the radar, which is useful within just 1 light hours. If we are going, if the object is farther away than that, then the parallax method is used, which is useful within 200 parallax parsecs. Now, if the body is farther away than that, and the distance to it is lower than about 10,000 parsecs, then the spectroscopy parallax or HR diagram fitting method can be used. Now, these are the three methods which can be used to calculate distances to solar system objects or the Milky Way stars. Now, if we are going further to calculate distances to the galaxies, then these are the four methods which can be used. So the Cepheid variable method is useful within 25 million parsecs. If the object is farther away than that, so one has to use the galaxy rotation rate, which is useful within 200 million parsecs. For an object farther away than that, one can use the type 1a supernova explosion method, which is useful within 1 billion parsecs. And the Hubble's law method is useful beyond 100 million parsecs. So now these are the methods which can be used or which are in the use to calculate distances to celestial objects. So in the upcoming videos of this series, we will discuss about each of these methods. So stay tuned. Bye bye and stay safe. Bye bye.